by the window there, Jack? I just wondered if you could turn the channel A on. I think Al can get it, though. It's right behind him, too. Never mind. Just turn that recorder on, yeah. Do you? Okay. Okay. I've already got it, Jack. Thank you. Let's talk for a little bit about spinning objects in zero-G. Some of you may have seen our attempts to spin little drink bags or drink bottles or things like this. And it's always a little difficult to get them oscillating and spinning without imparting just a little bit of tumble at the same time. But we have found a more convenient way to set objects spinning. And to illustrate that, I'm going to borrow part of the apparatus from one of the student experimenters. This is the device that really belongs to Vincent Converse from up in Rockford, Illinois, and we've used it before as a means of measuring mass. It puts a mass on the end and then the vibration of the spring. I'd like to borrow it for another purpose right now and show how we can use this large bolt and nut for the purpose of a launching platform. Now these are large masses, not too large. These are the masses at any rate that were used in the measurement of the period of this oscillation. Let's take a look at what happens when we spin them off. As you can see, they spin off this bolt very freely, and the nut then continues to spin very, very smoothly and stably in space. You see, once again, it continues to spin pretty nearly stably about the direction in which it was launched. Now you can see a little bit of wobble there, and I'll try to explain that in just a minute. But the next thing I want to show is when I tip these in a direction perpendicular to that. If it's not spinning, watch what it does. You see it spins right over and turns parallel to the Earth's field so that its spin axis, or its axis through the disk, is oriented with the Earth's field just the way it was before. That's its normal tendency, is to tip right over and align its own dipole with the direction of the Earth's field. Now I'm going to spin it about this direction, and we'll see what its reaction is. All right, now it's more or less spin axis perpendicular to the Earth's field at this point. Well, we have to watch it for just a minute here, but the thing that I want you to observe is the fact that its spin axis is tipping over in another direction. You see, now it's now tipped over to the point where it's almost facing the camera. And now it has. It's tipped about 90 degrees, but not toward the Earth's field, which is off to my right. Instead, it is tipped over towards the camera. Now, this is called precession. And it is produced by the fact that whenever we have a spinning object and we try to torque it or twist it in a direction perpendicular to its spin axis, then it will actually react by tipping in yet the other orthogonal direction. And it has caused, in this case, the spinning disk to precess perpendicular to both its original spin direction and the direction of the Earth's magnetic field. So that's a property of gyroscopes that can be observed and is observed on the ground. But it's not quite as conveniently observed as it is here in zero-G because we have no other forces acting on our gyro, in this case, the spinning disk. We don't have any gimbals that have to hold it, and there's no other perturbing factors here in zero-G. I'll try that one more time. There it is spinning, and instead of tipping over toward the Earth's field, you can see it's beginning to tip toward the camera, precessing 90 degrees from the direction that it would have if it had not been spinning. There it's precessed about 90 degrees in those few seconds. And it will continue to spin right on around, to precess right on around in the direction that it's going. Now it is precessed almost 180 degrees. Now we'll go back and check the Earth's field once more. We'll see whether or not it's changed. Take another of our little magnets. And it may have changed a little bit, but not a great deal in the time that we've been talking. But these magnets are already influencing each other, as you can see. And they'll align themselves just like that in the direction of the Earth's field. And as we saw before, there is no precession. Okay. We'll try to spin it with this extra little magnet on top. It has to be very precisely aligned with the spin axis, or the extra little perturbations that it gives us cause it to wobble off to one side like that. Now you can see this very strange behavior. I'll try to explain what is causing this, and it's related to that little wobble that we saw before. You see, it'll spin pretty stable for a few seconds, and then it'll stop. It'll tumble all out of direction, and then it'll stabilize again. Now, if you can explain this properly, why, it'll probably be a very challenging task, but I'll give you a clue, at least to what I think the explanation is. The torque, in this case, is not directly about the center of mass of that spinning disk. The torque is way out to one side, because I have the dipole, you see, sticking quite a ways on out. And that causes the whole gyro essentially to tumble after a few seconds. And it'll tumble in the way it is, whoops, it just stabilized again. But that's a rather complicated problem to analyze, I suspect. And if you'd care to try a thorough analysis of it, why, I'm sure there'd be some people interested in the solution that you came up with. Now, you think anything else that comes to mind, a question left in your mind, Al? Okay. Okay, that's the end of this one, folks.